Hello, we're going to talk today about the Fibonacci series and its closed form. It has a closed form, but the closed form is not used in competitive programming. So competitive programming, there's a question that shows up which says find the nth Fibonacci number for a large value of n, and people don't use the closed form. They use something else. Why is that? Typically, the closed form solutions is very efficient. So first, let's talk about the Fibonacci series. What is it, right? So it goes something like this. The 0th term, we start at 0, is 0. The 1th term or the first term is 1. And from here on out, you use this formula, Fn equal to Fn minus 1 plus Fn minus 2. So the second term is going to be 1 plus 0, which is 1. The third term is going to be 1 plus 1, 2, and then 3, and then 5. 3 plus 2 is 5, 8, and so on. And you can see these terms are going to increase very quickly, and they're going to start, blowing up. But that's okay, right? The question is that you're given n, and you need to write a function in a computer which takes n as input and gives you the Fibonacci number as output. So f of 3 would be 2, f of 4, 5, 6 would be 8, and so on. And we need to do this efficiently, right? And this is also an interview question, by the way, that shows up in tech interviews. And it's tagged as an easy question on lead code, and I'll share the link to the lead code interview question in the description. And and so you're likely to see this in data science interviews because the bar is on programming is slightly lower there. So the first thing you can do is you can just leverage this recursion, right? And this recursion only holds when n is greater than 2. Otherwise, what you have is fn is just n conveniently, right? Otherwise, because we see here that when f0 is 0, f1 is 1. But from here on out, fn is basically the sum of the previous two terms. So we can already use this recursion and write a neat Python program. Here, this is a blog. The video here is based on this blog, and I'll share the link to this guy in the description as well. Okay, so let's look at the Python code very quickly for the recursive version, right? So when n less than 2, we just return n. When n less than 2, right? Otherwise, we return Fibonacci n minus 1 plus Fibonacci n minus 2. And this will work, right? This will give you the nth Fibonacci number if you plug n in. Except that there's one small problem, which is that this is very inefficient, right? So let's think about calculating f of 10, right? What you'll do is first you'll say, okay, hey f, tell me what f of 10 is, right? Then what your recursive function will do is it'll say to calculate 10, I need f of 9, and then I need f of or let's say 8 and 9, and then for 8 I need 6 and 7. For 9 I need 7 and 8, and so on, right? Now I tried to draw this whole tree for f of 10 by hand, but you'll see here that I quickly ran out of space on the whiteboard and my hands became really tired, so I just gave up. And that really, it really it hammers in the point, right? That just to even for F10, you need so many calculations, right? So many recursive calls. And there's a lot of repetition here, right? Think about the number of times you're seeing 4, right? You're seeing F4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, a lot of times. And each time you see F4, this recursive method, just calculates it from scratch, right? It doesn't care that you've already calculated f4, so let me just use the previous value. So if it had just saved the previous value in memory, it wouldn't have had to recurse every time it needed to find the f4, right? If you stored the previous numbers, Fibonacci numbers, in an array, you can just calculate them the first time and then read them from the array. And this idea is called dynamic programming, where you have something recursive, but then you kind of save the values, right? The previous values, so you don't have to calculate them from scratch every time. And so if you do that, you will get a method that is, instead of exponential, here you can see this method was exponential because this is a tree. The height of the tree is n because you go from 10 all the way to 1, right? If you get from 1 or 0, get to 1 or 0, that's when you can just return n. Otherwise, you're still recursing. And at each time this tree branches, there are, it doubles the number of leaves, and then there are n o of n time branchings, right? And so it's roughly 2 to the power n. In reality, it's more like 1.6 to the power n, or like in terms of big O notation. But it's exponential, right? And that's the point. And we don't like exponential. It'll become very inefficient very fast. So this is no good. We can use dynamic programming, like I said, by saving the previous values in an array to make it on. But actually, you don't even need to save all the values, all the previous values, because when you're calculating f of n, you just need the previous two, f of n minus 1 and f of n minus 2, right? So at every step, you can just save the previous two numbers and not and not the whole area, and discard the rest of them, right? And that way, your solution becomes o on time and o1 space, because you're only storing two numbers at a time, right? And there's a very nice implementation here that I took from a Stack Overflow answer, which just says, you start with AB as 0 and 1, and then you loop n times, and then you say AB is B comma A plus B, right? So basically you say, you start with, A as 0, B as 1, and then you say A becomes B and B becomes A plus B, right? And you do this, and then you get, in your first iteration, this b dash will be 1. In your second iteration, b dash will be 2. And if you do it n times, you'll get the nth Fibonacci number. And so, this is a nice clean solution, which is on in time and o1 in space. It stores just two entries. And if this comes up in a tech interview, this will be it. No one will expect you to do more than this. And then they'll just move to the next question. But we can do better, right? In reality, we can do better than this this on time, right? And that's where the closed form comes in. And how do you get the closed form, right? The closed form meaning that you can just write the formula on a piece of paper, just given this expression, right? Given this rule. So the way you do this is with generating functions, right? So a generating function is a nice trick where you say, you just define a function f of z, right? So this is the generating functions method, is equal to f of 0 times z to the power 0 plus f of 1 times z to the power 1 plus f of 2 times z square, and so on, all the way to infinity, right? This is infinite terms. For most values of z, this will blow up, but that's okay. That's how we're defining the function. And then we can kind of write this more succinctly as capital F of z equal to summation f of n times z to the power n, with n going from 0 to infinity. And that's what you see here. And then what we can do is we can just plug in this recurrence, right? We know that f of n is this stuff, right? So we can just plug this in place of f of n, and then we'll get an expression for capital F of z. And then we can solve for it and we can get f of z in closed form first, the generating function in closed form, and from the generating function we can get the Fibonacci number as well. Now, one thing to keep in mind is that when you're doing this trick, this is something I keep forgetting when I come back to this a year later or whatever, is that you have to kind of separate out the first two terms, right? And the reason is that you'll basically get when you plug this in, you'll kind of try to reindex and try to express it as f of capital F of z again. And so you don't want, when you do the reindexing, right, of this the index that's in the summation, you don't want the f of -1 and f -2 terms, because you won't know what to do with them. This series is defined f0 onwards, right? For that reason, to avoid that, you say, okay, let's take out the f0 term, let's take out the f1 term, and then make the summation go from 2 to infinity. And then you have this fn becomes fn minus 1 plus fn minus 2, right? And f0 is just 0, so this goes away. And f1 is 1, so this becomes z, right? And then you can bring this z to the power n inside, and you get these two summations, right? Fn minus 1, fn minus 2. And now you can take one of the z's outside, right? And then you get fn minus 1 z to the power n minus 1, and here you take two z's outside, right? And this is where the reindexing thing comes in, and you'll see why we kind of separated these two terms out, because now we can just say let n minus 1 be something else, right? Let n minus 1 be m, and then you get fm 0 to the power m, right? And the summation goes from, instead of going from 2, it goes from 1 to infinity. And because the f0 was 0 anyway, this becomes just f of z. You get back the generating function. And similarly, z squared times capital F of z. If you hadn't separated these two terms out, you would also have f minus 1 and f minus 2 terms when you did the reindexing, and that would have been a problem. So, this little trick helped us avoid that. Now you can just take all the fz terms to one side. You have fz here, capital Fz, and you get a closed form for the generating function, z upon 1 minus z plus z squared. Um, Using this generating function, you can see that the NS Fibonacci number through some algebra is the number of ways to create n using ones and twos, right? Add ones and twos together and create n. And I won't go into the details, but you can kind of see this from the geometric series, right? Don't worry if you don't see it right away. I'm going to link the blog so you can kind of look at it in more detail there. But yeah, that's something you already see. But apart from that, how do we now how do we now get the Fibonacci number, right? We got the generating function so far. We want the Fibonacci number, the actual small f of n, right? In order to do that, you first observe that this denominator is just a polynomial, a quadratic polynomial. And you can kind of, with any quadratic polynomial, you can write it as z to the z. It has two roots, right? The quadratic formula. And if you work out the quadratic formula, you'll get the two roots as, phi, the golden ratio, which is 1 plus square root of 5 by 2, and also psi, which is, 1 minus this phi, and that's 1 minus square root of 5 by 2. And so this 1 minus z plus z square term can be written as z minus phi times z minus psi. And now you can take this term and kind of split it up, right? Whenever you have a polynomial like this, you can kind of do a partial fraction trick and kind of separate these two terms out. And this other link kind of goes into the detailed math of it, where you kind of take this and then you try to express it as a by the first term plus b by the second term. It's a standard partial fractions trick, and then you find a and b, and you end up with this expression 1 by square root of 5 times 1 by 1 minus phi z subtracted by 1 minus 1 by psi z. And now these are just geometric series, right? 1 upon 1 minus phi z is 1 plus phi z square, and so on. And similarly for this other part, right? and then the closed form of the Fibonacci sequence is inside, because the nth Fibonacci number is just the coefficient of z to the power n in the generating function. So that becomes 1 by square root of 5 times phi to the power n, because z to the power n, over here there'll be a phi to the power n subtracted by psi to the power n, right? And this gives you the kind of closed form, right? Which we didn't need any computers to calculate this. Now, on the surface, it seems like we didn't gain too much, because if we want to code this up in a computer, we still have to raise phi to the nth power. And that requires n minus 1 multiplications, right? Because phi square is 1 multiplication, phi cube is 2 multiplications, and so on. So it seems like it's still an ON algorithm. But you can use something called fast exponentiation, right? One thing you'll notice straight away is that this psi is 1 minus square root of 5 by 2, which is the magnitude is less than 1, and this phi is 1 plus square root of 5 by 2, where the magnitude is greater than 1. So when you raise it to a large power of n, these two numbers, this term will just vanish because the magnitude is less than 1. And this is the term that will dominate, right? This will quickly become less than 1, and then it will just go to 0, right? So you can just ignore this part. So you just really need to do phi to the power n, right? And just round it down to the nearest integer after dividing by square root of 5. Um, uh, but multiplying it n times is on, but we can kind of there's a trick to make this much more efficient than on. And the trick is that right now you see you need n minus 1 multiplications, but you can write it, let's say n is even, you can write it as phi to the power n equal to phi to the power n by 2 times phi to the power n by 2. Now once you calculate phi to the power n by 2, you don't need to calculate it again. You can just calculate it once and then multiply it with itself. So the number of multiplications went from n minus 1 to n by 2 minus 1 plus 1, right? N by 2 minus 1 multiplications here, and then one more for the squaring. And so, you went from n minus 1 to n by 2 multiplications. So you cut the number of multiplications roughly in half, but then you won't stop here, right? You'll do the same trick recursively on phi to the power n by 2, and so on, all the way till you get to phi to the power 1, right? Or phi to the power 0. And every time you'll kind of, you'll be cutting the exponent down in half, right? Every time you do this. And for that reason, this will be a log n algorithm, because it will be exponentiate. It'll kind of branch down, and every time the exponent will half, right, at each step. And there's a Wikipedia article on fast exponentiation. The basic observation is that x to the power n can be written like this: x times x squared to the power n minus 1 by 2. So you just calculate x to the power n minus 1 by 2 and then square it. Or if n is odd, and if it's even, then you say x to the power n by 2 square, right, like we had up here. And then you can kind of just recurse, right? And you can say until the exponent becomes 1 or 0, I'm going to keep recursing, right? I'm going to keep splitting in half, and not do the second part again, right? So every time I reduce the number of multiplications by, I divide them by 2, and so this will become a log of n, O of log n algorithm. So this fast exponentiation trick will take us from O n time to O log n time, because we could do this fast exponentiation. So the closed form is much more efficient than the dynamic programming solution we had earlier. But then people don't use this; they use something slightly different in competitive programming, right? So in competitive programming, when they are asked large Fibonacci numbers, they use this trick with matrices, right? So first they write this recursion, right? You can just reindex by adding 2 to the n, and you get this, the old expression we had, fn plus 2 equal to fn plus 1 plus fn, right? And then you just add a dummy equation, right? Fn plus 1 equal to fn plus 1. And then you can write this in matrix form: fn plus 2 comma fn plus 1 equal to 1 1, right? 1 0, because fn plus 1 equal to fn plus 1 times 1 plus 0 times fn. Um, and you can make this, call this matrix A, and then you get this expression, right? And then what you can do is you can apply the same trick here, right, to this guy. You can go down to fn and fn minus 1 with another A, and that will become A square. And if you keep doing that, you'll end up with A to the power n, and you'll go all the way down to f1 and f0. And we already know that f1 is 1 and f0 is 0. So you can get your nth Fibonacci number this way. And now you can use the same fast exponentiation trick on A to the power n instead, right? And this is what people actually use. This is what people actually use in competitive programming. So why do they use this and not the closed form, right? In the closed form, you're just multiplying a scalar, which is the 1 plus square root of 5 by 2. You're raising that to the power n, whereas here you're raising this matrix, which is a 4 by 4 matrix to the power n. So raising this matrix to the power n will require, every matrix multiplication is 8 scalar multiplications, right? For a 2 by 2 matrix. So it's kind of 8 times worse. So why do people use it, right? It seems like in terms of big O notation, it's still O log n, sorry, just like the closed form, but it's 8 times worse. And the reason is that the reason is numerical issues, right? The phi to the power n term, as n becomes large, it's a floating point number, right? 1 plus square root of 5 by 2. And there's always some loss of precision when you raise these floating point numbers to large powers of n. And as n becomes large, if n becomes close to 100, those errors kind of compound, and they and the answer kind of diverges a lot from the true value. And the advantage of using the matrix is that everything is an integer, so you never leave the field of integers, right? You do a square, every multiplication you're doing is an integer multiplication. So you stay within the field of integers, right? In all the multiplications and additions you do. And so you never lose any precision. You never run into numerical precision problems. And that's why, even though this method is 8 times worse than the closed form, this is what actually ends up getting used. So that's it for this video. I hope you found this interesting. Thank you.